Hello again, and now finally we'll look at the detailed analysis of Pharmex data here. So we know that Pharmex is a drug chain, and they're looking at how the promotions and their sales quantify, how they're rated, where both of these are a percentage of that of the competitor. So let's do the analysis over here, and we can do it in R. So here's R. The first thing is R commander. Let me read the data in there. So data. We can import data from a text file, and so I'll just call this Pharmex. Okay, let's find the data. So the data here is in my lecture slides. There it is. Okay. So if I want to actually, the first thing I've done over here is a scatter plot. And I've got the other things on there, I won't bother with that. Let me just actually draw the scatter plot so I can do some graphs. And I've got here a scatter plot. And I'm going to put X as promote and Y as sales. And the options here I can what do I need here? Legend position, fine, alright, so I'm going to put a legend in there. And the squares land, I can put that on there as well. That'll be good enough. Okay, and there's my straight line plot. So you can see, basically the data has some variation, a reasonable amount of variation there. The maximum value seems for sales to be about 100, well, close to 120 odd. And the minimum is in the order of 80 odd. And promotions also go from a little below 80 till above 110%. But when we're spending about 110% or so, we're also getting 110% back just about. So this is the fit of that to start off with. What about actually running the regression? So if I go to the models and I go to, what's going on here? Statistic, and I'm going to go to fit models in a regression. That's all right. So my response variable is going to be sales and my promote. Okay. So here's the output. It tells you what I'm done. I'm putting sales against promotion over here. And so what you'll find here is it doesn't actually give you an another table. What it gives you is, first of all, the intercept. The value is 25.1264, and you can compare this with the calculations earlier. And promote is 0.76203. It gives you the standard errors of those things. It gives you the t-value, so it's basing these on t-test, and the p-value. So here's the p-value we had before, 8.59 times 10 to the negative 8. Now, the residual standard error here is 7.395 on 48 degrees of freedom. So this is our estimate of S on 48 degrees of freedom. And the multiple R squared is about 45%, or 0.4529. F-statistic as well before here. So you can put this in another table as well, but I want to do it over here. So this is how you can do this in R very fast. So there's the plot and some summary stats. So the maximum value for promote is 117%, and the maximum value for sales is 119% over here. So essentially, the data range for promotions here, I'm just summarizing the data here, is between 77 to 117%. And that's the mean, median 96.5. So that means that promotional expenditure exceeds that of the competitor for about half the stores. So 96.5 is essentially about for half the stores we get more than that. And also the sales range of 81 to 119%. Mean 99.7 and median 110. So the sales exceeds for more than half the stores, about that much. And the scatter plot here gives an R squared, or R of 6.6730. In other words, only 45% of the variation is explained by the regression. 45% is explained by the regression on promotions. Maybe there are other variables I can add to this as well to make this better. We don't know that yet. So here's the R output as we said before. As I was saying, here is my estimate of S with the degrees of freedom, So these t values here will be based on the t48 distribution. And these standard errors over here are also based on this s and some other thing. And this standard error we saw earlier, which we worked out was s on ssx square root of, that's what this comes to here. You find two r squares here, multiple r and adjusted r squared. So this is something we'll see afterwards. Hypothesis test. Now, because I actually have t values here, these are always two-tailed, two-sided hypothesis test. So for the two-tailed test, I can go ahead and do it as before. For the one-sided, I will simply just halve the p-value as we did before. The confidence intervals you can work out fairly easily. There's a command called confint, and you can put in the actual linear model you fitted. So if I look at the R, the linear model I fitted here was, what it had called it was a reg model 1. So if I put in here reg model 1 instead of farmex.lm, I'll be able to get the confidence intervals of both of those. So this we had done calculations on earlier. You can check the calculation. And for intercept also sometimes that's an important thing to calculate as well. Finally, I can perform or find the n over table as well by putting in this command n over with farmex.lm as the model. And here we had reg1.lm that we fitted. And so in this case then, what it will give me is the n over table. You can compare the calculations we had here with before. And again, the p-value here with before. Diagnostics of the model here. Histogram looks okay. This is deep over here, but that's not serious. No probability scores are fairly straightforward over here. No change in speed. So all the model assumptions of equal variance, of the linear model being appropriate, and also of the normality of the residuals of errors is all satisfied in this case here. And essentially I've just said that over here. Also there are no outliers in data. Predictions are easy. All I've done is here I have put in the values for the model that I want to predict, and I've also put in essentially this is my data frame, but when I put in here this new as what I want to predict at, it predicts at all of those simultaneously. Well, this is for promoters 80, promote 85, 90, 95, 100, 105, and so on. Fairly easily done in R. Now here's another last example before I finish. Here is the output of a regression analysis of y against x. What you find is the p-value here is very small, and so the correlation coefficient also is very high, 92%, higher than farmex. So that would indicate to us that this is a very good, strong relationship between x and y. But it does not prove that the relationship is linear. You only know that if you perform the diagnosis of the model. So by all means over here that I've listed here, it looks like it's a very good relationship. It's not a good one unless you actually perform the model diagnostics. Look at the diagnosis of the model over here. You can see there's a symmetric pattern here. All the points above, then below, then above. And if you look at residuals against predicted values, you find certainly a very strong relationship that way. Some kind of pattern there. And so the normality ideas won't work because of the problem with the model itself. In fact, what's happening is, you'll be able to see it's actually clear, y equals x squared is what's indicated. This is a parabolic shape. So the residuals plots indicates to you what is missing in the model and what else you need to enter in the model to improve the model. That's why residual plots, once the model has been fitted, this is the most important thing. This is what's left in the data after you've extracted the relationship that you have fitted. So when there's something else left in the data after that, in the residuals, it'll show up. So here an x squared term is what's required. If I actually put an x squared term over here, you'll find the model fits perfectly. As a summary here, these are the things we should be able to do. In a regression model, explain the terms, prepare the neighbor table if you have to, perform hypothesis tests, confidence intervals, predict, and also know when the prediction is reliable, and some relationships. So coming to predictions, you can only predict in the range of data. So if my x values go from here to there, then this is the range I can predict in. Any values outside that will be a problem. So the problem is if I've got some data that looks like that, and I fit a linear straight line to this, and now I'm trying to predict what's going to happen here. So this is my range of data, that little bit there. These are my x values, and these are my y values. If I predict for a point over here, I don't know what's going on. It could be the data actually, the model actually looks like this. And I've just seen this part of it. So prediction outside the range is going to be unreliable. The further out I go, the more unreliable it's going to be. It's best to try and stick with predictions within the limits of data. If you go outside that, then you'll have the caution that you know that the predictions aren't so reliable. In fact, you can work out in these situations what's called a prediction interval. We won't go there this time. Thank you very much.